Hello, everybody. It's time for another great day of chemistry. So last time we looked at how we could improve the ideal gas law by doing a brute force expansion to correct for failures of the ideal gas law under high pressure scenarios. This time we're going to be looking at a little bit more elegant of a solution. So one of the things that we can often do is instead of doing a brute force correction where we keep adding in corrective terms by fitting it to empirical data, we can instead use chemical intuition. And this is going to be an approach that I tend to prefer, but can often be harder to do, as you'll see with our end result. So one of the things we can do is take a look at when the ideal gas law fails and try to include additional terms to correct for those specific occasions. So one of our first failures is that we treated the ideal gas as essentially hard as point particles where we were able to ignore the volume of the gas. The problem is under very high concentrations, real gas molecules take up real volume. So what we have to do is exclude the volume occupied by the gas molecules from the volume of the container. And this instead produces something called the effective volume. So this is the volume that the gas can actually move around in, as opposed to the volume in the container. Under low concentrations, these two should be the same. But as we get to higher and higher pressures, so lower molar volumes, this extra term of the space occupied by the gas tends to become a lot more important, where again, N is going to be the number of moles of gas, and B here represents the molar volume of the gas. So essentially, what volume would 1 mole of gas, when ultra compressed together, take up? So if you know how much gas you have and you know the space it occupies, the rest is going to be the free space the gas can move around it. So what we can then do is again just treat this volume in the ideal gas law as again the effective ideal volume, and then just subtract out the space occupied by the gas. And what we're going to notice here is as that n gets larger, this V term is going to be a lot smaller than expected under ideal cases. So that means under those high pressures, which is again high concentration, it means that that pressure is going to be a lot larger than expected because again, this term gets smaller than expected, and because of ratios, we end up with a much larger pressure, which again is exactly what we'd expect to see in those high pressure scenarios, that we see that positive deviation with the Z greater than 1. So this is a good way to account for that volume correction that we spend a lot of time with on the virial. Unfortunately, there was another failure we ran into, and that's the fact that we assumed that our gases were again hard spheres, and we ignored any attractive features. So the other term we have to include is that what do I do if I have attractive intermolecular forces? Well, if the gas molecules are going to attract each other, as we saw when looking at the compressibility factor, that will reduce the pressure exerted on the container because the gases are clumping, and that means that we essentially have a lower effective concentration, or again, lower pressures. So what we can do is account for the intermolecular forces using a term based on a prefactor and the squared concentration. And again, we're typically going to use this concentration in molarity or moles over volume. So you can rewrite this simply as the mole squared over volume squared, or if you prefer, the molarity squared. And the reason why is if we're looking at the interactions in between two molecules, we have to use their concentrations squared, as this will dictate how likely the gas molecules are to encounter. Under very high concentrations, they're going to be much more likely to encounter each other than under very low. And we can go ahead and prove this later in the semester when we get to describing kinetics of interactions. Now, A here, this is going to be an empirically fitted parameter. So just like B constitutes the size of the molecule, which we can go ahead and fit, A is going to be a little harder. We're going to need to analyze this specific gas to figure out the strength of its intermolecular forces. But note, the strength of the intermolecular forces will show no temperature dependence. So once you go ahead and fit this, unlike the virial, this will work for any occasion. And that's going to be makes the van der Waals equation a lot more robust. So again, we know that we can model the intermolecular forces by A times the concentration squared. But since this reduces the pressure, we can go ahead and add it in on the end, where it will just lower the pressure predicted from this original term. So congratulations, we put all of this together and we've now generated something called the van der Waals equation. And what we show here is that as we have a molecule with stronger intermolecular forces, this will reduce the pressure of the system, giving us again that negative deviation from ideality, or a z less than 1. But notice, compared to the virial, when I go ahead and construct this equation, we don't have a direct one-to-one comparison of a single parameter or even set of parameters and the z. It's a little bit more holistic in nature. So congratulations, we now can combine these two terms together to get the van der Waals equation. Now, this is often the form that I like looking at because it gives you a direct metric and several variables we can tune, most notably concentrations and temperature. However, this is typically not the way this equation is going to be presented. It's much more common to see this equation presented by separating out these pressure and volume terms. So again, we add the pressure correction to both sides, and then multiply V minus NB onto the other side. And this makes it a little more clear to see that we've modified the ideal gas law, where again, we have this correction to the pressure term. Again, note that if the pressure is lower than expected, has been reduced, this is essentially modified by this would be the ideal pressure. Some of it comes from this attractive term, and some is going to be the one we actually measure. And again, same thing with the volume. And all of this is still equal to nRT. However, note here, we have to know both the moles and the volume of the system separately. And that gets a little bit more tricky to handle. So instead, this equation is often rewritten in a molar volume notation, where in this case, we divide everybody by n. That mostly gets rid of the n here, but most notably, it turns this volume term into molar volume and gets rid of the n here as well. So when we do this, we now have our pressure term instead of concentration, or over the attractive property divided by the molar volume squared, molar volume minus B. So notice now we only have two molar volume terms, which makes it a little bit easier to handle. And again, that molar volume can be easily converted from other metrics like density or molarity or other forms of concentration. So this gives us a fairly general equation of state for a real gas. And again, our only variable dependencies are pressure, molar volume, and temperature. So same thing we saw with the ideal gas law, but we've now introduced two parameters that are going to be non-temperature dependent. Our A, which is going to stand for our attractive intermolecular forces, and our B here, which is going to stand for the size of the molecule of interest. And this works actually fairly well, and it's a fairly reliable equation, even if it's a little bit more clunky to work with mathematically than the virial system. And it's worth noting it works very well, but there's again one point at which we expect to see this equation to fail, and that is at temperatures below the critical point. So again, note if we're in a temperature below a critical point, and again, at relatively high molar volumes, we run into a slight problem when we look at our isotherms. And that's the fact that we start to form either a liquid or a supercritical fluid. So not too surprisingly, we wouldn't expect a single gas equation to model a liquid or critical volume very well. And not too surprisingly, the van der Waals equation does fail under these occasions. And if we look at the isotherms, it will produce the experimentally relevant isotherms all the way up to about the critical point. However, once you get below the critical temperature, and again, these small molar volumes, something kind of fun happens. Whereas instead of having this flat behavior to demonstrate the pressure of a gas over a liquid, it generates this oscillation where the pressure goes up and then goes down. And we would not expect the pressure to go down as the volume increases. And there's a reason why, that we have a mathematical failure at these subcritical temperatures. And so Not, so again, this is just going to be a failure of the van der Waals equation and something to look out for. The moment you see these van der Waal loops, congratulations, you're now below the critical temperature. So something to keep an eye out for. However, conveniently, there is a correction we can use. So there's something called the Maxwell construction. So this idea, you can't have these oscillating van der Waals loops, but instead what you can do is go ahead and draw a straight line across the isotherm that essentially has equal areas in the area above this line and below this line. And if you replace these two equal areas with a straight line, that will actually tend to replicate the realistic isotherm. So even under this area of major failure, we still have a fairly robust depiction. Again, showing the van der Waals equation actually does work fairly well. However, you can take this same idea of the van der Waals equation of doing realistic corrections to an experimental system and take it a little bit further. So while the van der Waals equation is generally going to be good enough for most of our purposes, if you get to really lower temperatures or higher pressures, it also will begin to fail. And you can add some additional terms or parameters to go ahead and correct this system. So one example is you can construct what's called the Redlich-Kwong equation. So in this case, the volume term looks relatively similar, but you go ahead and correct the attractive term by essentially correcting the molar volume to indicate a temperature dependency, which again, experimentally makes sense because we know that at low temperatures, we're more likely to have higher attractive properties. So this again will help improve the system. There's also the Pang-Robinson approach, where instead of having to deal with temperature, you can add in a more complex molar volume relationship to that attractive properties, which again will better mimic reality. And we can go ahead and compare these three different approaches versus experimental data. And what you'll see is that all three approaches tend to replicate the experimental data at fairly high pressures. Again, this is going to be a pressure, a molarity for the gas um, of up to about 5 moles, or about 6 moles per liter. But past this point, the van der Waals equation just does start to break down. However, we see the Pang-Robinson approach actually works up to 12, so very high concentrations, and the Redlich-Kwong even further. And again, this is all going to be for ethane. So again, most of the time, van der Waals is good enough, but if you're talking with some really extreme conditions, there are several different much more effective methods that, while mathematically more cumbersome to work with, does better mimic reality. So next time, we're going to go ahead and look at a way to compare uh, several of our advanced models across different gases to make a more robust system. Until then, take care.